Use weight.
Like take up space.
Okay. So let's say I have a penny. So imagine I'm holding a penny here, and I have hydrogen gas in this hand, and the hydrogen gas and the penny weigh the same amount. Which one's going to take up more space in my hand? You have to visualize. I can't show you.
But you can't. Yeah, you can't show it though.
Right.
But that's going to take up more space
because it does this. What's that mean?
It's spread out.
Very good. So if you have two things that have the same mass, the one with the lower density takes up more space. What's that called? The amount of space something takes up. Say it again. Volume. So gas is spread out. That's what low density means. The particles that make up that gas are very far apart. So that's what low density means. Okay. So gas particles, very far, very spread out, take up a lot of space. Provide a little penny, particles are really close together because they're solids. They're very dense. Okay. That and this could have the same mass, but it takes up more space because it's less dense. All right. Good. Hydrogen, helium, fluorine and chlorine, bromine and iodine. So group 17 is the only group on the chart that has all three phases. Two gases, a liquid, and solid. So that's just kind of FYI. Let's see. Oh, what can iodine do? What can iodine do that no other elements can do? That's why it has this special cap on it. A special cap on it right here. Sublimes from solid to gas. Right. So that's something you need to remember. And I am going to show you that. Okay, not today, but I will get that set up so you can see that. All right, and that's it. Okay, so we talked about some of the individual elements. Next thing I need to talk about quickly with you are the 7 diatomic elements. 7 diatomic elements. These elements do not exist as atoms, they exist as molecules. What the heck's the difference, bless you, between an atom and a molecule? I'll use these magnets to explain. Bless you. Okay. So, that is an atom. That is a molecule. So, don't write this, just watch. So, this would be, let's say, calcium. Calcium exists as a whole bunch of atoms very close together. So calcium, might as well just show you the whole thing here. Calcium, let's say each red one was a calcium. It's a solid, so the particles are orderly, very close together. Matt Payne, double check. Can we see this over here?
Yeah.
Yeah? Okay.
Yeah.
Okay. So that's calcium. Individual atoms. Atoms are like little round spheres, right? Protons, neutrons, electrons. So calcium atoms very close together, that's a solid. Well, there's 7 elements. Out of all the elements, there's only 7 that they don't exist as atoms. They exist in pairs. That's called a molecule. So, let me use a different color actually. There for a second. So, over here, this is what a diatomic element would look like. Okay? So 2 atoms touching is called a molecule. If you don't know this, you need to write this down, that one single circle. So we'll say that's an atom, and then 2 together is a molecule. You do need to know that. 7 elements exist as molecules. They never exist as atoms. And those 7 are called the Honkelbriefs. That's the acronym for it. Honkelbrief. Sounds like some weird uncle. Uncle Honkelbrief. Anyways, what are the elements? Let's spell it out. Honkelbrief. Hydrogen, good. H. Oxygen. Nitrogen. Honkelbrief. Who's coal? Chlorine. Capital C, lowercase l. Bromine. Capital B, lowercase r. If. Honkelbrief. I, iodine, and chlorine. Those are the 7 elements that are called diatomic. So underneath each element, the bottom right, we're going to do a subscript. Subscript 2, H2, O2, N2, Cl2, Br2, I2, and F2. All of those elements exist like this picture right here. So why don't you sketch this somewhere in your notes to the side or underneath it. Not this one. This is what they kind of look like. These are all gases except for Br, it's a liquid. So if we were to draw a liquid, we just push these a little closer together. But right now, this kind of looks like a gas. Molecules are very spread out. That's how these 7 exist. They are extremely reactive if they are by themselves, so they combine with themselves, which I'm glad they do, because if O2 didn't do that, we wouldn't be able to breathe. You can't breathe just O. You need O2. So these are diatomic. You need to know that, memorize them, but also understand what a molecule kind of looks like. Okay? So from now on, if I say hydrogen gas, oxygen gas, you're not thinking H and O, you're thinking H2O2. All right? So these are called the diatomic elements. And Honkobriff is just a weird little word to help you remember it. That's all. Questions on that? All right. So we are done with the periodic table. We've gone through all the names, all the groups, explain the atomic number, metallic character, non-metallic character, right? Metals, non-metals, metalloids, properties, some individual elements, the carbon allotropes there. Now the diatomics, nuclear symbol we've talked about. Maybe we should actually get an example in our notes. I don't think we actually have one in our notes. Let me get that down. So a nuclear symbol. So we'll just pick, we'll pick another one you need to know tomorrow. Who knows the symbol for plutonium? That is on the quiz tomorrow. Pu, very good. Pu is plutonium. What is the mass number of plutonium? Aaliyah, what's the mass number of plutonium? Check all the way at the bottom. Yeah, the mass, yep. 244, so that goes in the top left. 244, I'm just going to label that. That's called the mass number. It's not called the atomic mass because the atomic mass has all the decimals. Pu actually doesn't have any decimals. I'll explain why down the road. So this is always a rounded number. Pu doesn't have any decimal points, but if it did, you could round it to a whole number. Tyler, what's the atomic number?
94.
94 goes in the bottom left. Here's the atomic number. And that tells us the protons and electrons in a neutral atom. That's called a nuclear symbol. So you do need to know that as well moving forward for like the whole year, basically. Questions? Okay. So we're moving on. And you know what? Maybe I should actually address that whole number thing. Just briefly. Feel bad if I bring something up and then don't explain it at all. So everyone look to the side here. Alright, see these numbers down here? Everyone look over here, please. You got RF all the way through UUB. They're all whole numbers in the red. Same thing, all whole numbers. But everybody else, pretty much, TC's a whole number, but everyone else has decimal points. Anyone want to have a, and some of these here, these have whole numbers. Any theories out there why the mass of some of them have decimal points and some they don't? The ones that are man-made are all the ones that are outlined. Yep, that's one reason. So on your report card, does it give you your overall average? So you have like, you know, a 95 in chemistry, 84 in English or whatever, and then at the end it gives you your overall average, right? Is it always a whole number? Why? If you don't have decimal point grades in the classes, why is the overall average maybe have a decimal point? So you have a 95, 84, 82, 80, 78, whatever. Add them up, divide by the number, write your averaging, and then you get your average. Why does the average have a decimal point?
If they're trying to find the weight, did they have like multiple ones? Maybe.
Wait a second, Matt. Let's answer the question about the grades first.
Oh.
You're getting way out. You're ruining all my fun. You're skipping the race. You got to do the race first, then get to the end line. Well, the answer is because you're averaging. It's kind of like an obvious answer. It's hard to answer that. You're averaging. Anytime you average, there's a good chance of having decimal points because you're averaging 5. You guys are what? 6 classes? 10, 8, 9, 4, 5. How many classes you guys take? 6? 7. Okay. So you're averaging 6, 7 classes. And when you do that, you average 7 numbers and divide by 7, you're probably going to get a decimal because chances of being a whole number is probably pretty rare. So what were you saying?
If they've like weighed the element or something like that, if they found the mass of it or whatever, like multiple times and it was different times.
Very close. So let's take calcium, for example. You find a sample of calcium and another sample of calcium. This one has a mass of 40, this one has a mass of 41. If you average 40 plus 41, what would you get? So it's 81 divided by 2. 40.5. Would you agree? So the average would be 40.5. That's why those have decimal points. These things are called isotopes. There's more than one isotope of almost all the elements up there. What does that mean? If you find the element in nature somewhere, and it's in a compound usually, but if you find the element in a rock, in a sample, there's going to be different masses of the same element. So this is calcium, and this is calcium. They're both calcium. This one has a slightly larger mass. So to get the mass on the chart, they take an average. It's called a weighted average, actually. Weighted average of the naturally occurring isotopes. What does weighted average mean? Well, maybe this one is worth like 60% of the overall mass, and this is worth 40%. And where does that percentage come from? Well, in the world, 60% of the calcium on the planet have this mass, and 40% of the calcium have that mass. So like in here, your quizzes are worth 60%, and then your homework and labs are the other 40. So if you do really well on quizzes, not as well on homework and labs, this will help more because it's weighted more. So that's where those decimals come from. The ones without a decimal, like PU, only has one sample and it's a mass of 244. It only has that one sample. It's not a weighted average. Okay? That's kind of a lie, actually, because there are other isotopes of PU, but the ones that are synthetic, they don't have a naturally occurring isotope, so it's a little different with those. So anyways, that's where the decimal points come from. If you did not follow me or you're confused, that's okay. We're going to go through that again. But I feel like I should bring it up because I mentioned it. All right, moving on. Okay, now I'm going to walk around with these and you can just look at them. Isn't this fun? Notice the difference between them. Come up with a difference between these two. You've already seen these. Just look at the two of these here and see the difference between them. All right, that was fun. Okay, so you have the beaker and the graduated cylinder. The beaker and the graduated cylinder. What's the difference between these two? What was I showing you? One's used to measure what? Volume, good. Which one's that? Right, we use this for volume. For all you viewers at home, we use this. We don't use this. Why? Not exact. Ah, I have a better word for that. It's not as significant. Write this down. Significant figures is the next thing we need to learn. And I will be honest with you, it's not super exciting, but it's something you do need to know. So I do it right at the beginning of the year because we use it all year. This is a more significant measure of volume than this. Adam, why?
It's more precise.
Why is it more precise? Right. What are those little marks called?
Measurements.
Close. Anyone know? That's with a G. Graduation marks. More graduation marks. So, more graduations. So, yeah, a graduated cylinder, you don't have to write this, but so the graduated cylinder here has all these lines, right? And then a beaker has like that many lines. So from here to here, let's say that's 0 to 50. Let's say this is 0 to 50. So we have 1, 2, 3, 4, 5 lines to measure 50 milliliters. Here we have like 20 lines or 50 lines. So the more marks that there are on the measuring device, that means each line is worth less volume, right? So maybe each line is 0.1. Over here, each line is worth like 5. So if I want to measure 5.5 milliliters, that's easy to do here. Here, you're just guessing, because this line is 5, this line is 10. There's no lines in the middle. So 5.5, where would that be? Just a little bit over 5? That's a crappy way to do it. So this is a more significant measurement. So this would measure to the whole number, like 5, 10, 15, blah, blah, blah. This one would be like 1, 1.1, 1.2, dot, dot, dot. So you would go up by a tenth. This number, 1.2, versus the number 5, this number is more significant. It has more significant figures. This number has 2, we call it sig figs. You can write this down, 2 sig figs. This has 1 sig fig. That's just the abbreviation for it, or 1 sig fig. So a significant figure is used to kind of validate your measurement or your tool or piece of equipment you're using. Which one is going to be a better piece of equipment for whatever you're measuring? Are you measuring mass, volume, density, you know, whatever? Length of something. If I wanted to measure the length of this room, what would probably be the best piece of equipment or tool we could use? So from this wall to that wall. Would I use this? A meter stick? Would I use a ruler? What if I measure this marker and I knew how long the marker was and I used the marker to measure the length of the room? Out of these three, which one do you think is more significant? This one probably. Okay, be easier to use, but I don't have an example of this. What would be the best thing to use probably for this room? Tape measure. Yeah, maybe like a 100-foot tape measure. Okay, so that would reach the entire length. And it would probably have a lot of graduation marks. If you ever see a tape measure, some of them definitely have a lot of graduation marks. So the more numbers in the measurement, the more significant it is. Okay? So let's say you had a scale that only measured in 10-pound increments. Okay, we all got on a scale, and we're all somewhere between 100 and 200 pounds. But maybe someone's 118 pounds and someone's 111, you get on the scale, it basically say the same thing. If it only read 110. Doesn't make any sense. It's not very significant. So we want more numbers means more significant. So what we're going to learn right now today is how can you tell me, if I write a series of numbers on the board, how many significant figures it has? And what is this relating to? In chemistry, there's certain pieces of equipment that are more significant than others. So that's the point of learning this, is in real life you can apply it. This is more significant, there's more numbers here, more decimal places perhaps, less numbers, less significant. Hopefully that makes a little sense, because sometimes when I teach this, kids lose the meaning and the purpose, and they're like, this is just stupid. Well, there's a reason for it. I'm trying to explain that. So if I was to write 1.2 on the board and 5 on the board, I hope you guys can understand this has 2 numbers, therefore 2 sig figs. That has 1 number, just 1 significant figure. So this is a more significant measurement. Does that make some sense to most of you, hopefully, that if there's a tenth here, it's a more significant measurement? It's more accurate, more exact? I hope so. Okay, so now, before we move on, a little geography lesson. I don't even know how to draw, so I'm just going to write USA. Okay. There's our country, okay, right here. If you want to draw a little, Florida and all that jazz, go ahead. So, Here's our country. Over here, just to make sure we know, here's California and here's New York up here. Just so we understand what I'm trying to draw here. All right. So, Europe's over here. You keep going far enough this way, Asia's over here. What's this ocean called? What's this ocean called? Raise your hand. Watson. Right, here's the Pacific, right? Pacific over here. And the Atlantic over here. Good. Good job. Hopefully everyone knew that. Okay. In chemistry, in terms of significant figures, we use this to help us understand how to count the number of significant figures. So really pay attention. It's the first time I explain it is the most important. Okay. So in place of the good old US of A here, we're going to imagine there's like a number. So I'll give you a number. Let's say we have the number 200.06 centimeters. Write that down. Let's say that's the number. Underneath it, we're going to write another number. I'm just going to put it a little bit higher. 200.06 centimeters. And then we're going to have the number just 200 centimeters. So we have two numbers. One number has a decimal point. The other number does not. So this area here between the oceans, that's where our number goes. Now, Pacific stands for, really it's just the P we're getting at. That stands for present. And then the A stands for absent. And when I say present and absent, I mean decimal point. Is the decimal point present? Is the decimal point absent? If the decimal point is present, really pay attention and look up here. If the decimal point is present, we look at our number and we go over to the Pacific side of the number. Because remember, the number is like the country. So on this side is the Pacific. If the decimal point is absent, we go to the right side, that's where the Atlantic is, the A. So decimal point present. So we start over here on the Pacific side. Go ahead and draw that arrow. I'll explain in a second what that means. If we're here in this type of number, decimal point is absent. We go over to the right side of the number. The arrow tells us how to start counting the significant figures. So here we go. If the decimal point is present, you start on the left side of the number, because that's where the Pacific Ocean is, the left side, right? The west coast. So here's the west coast. Now, here's the only rule you need to remember once you figure out which side you're on. Once you figure out which side you're on with the decimal point absent present, there's only one rule. You start counting significant numbers, significant figures, with the first non-zero number. So if this was a 0, we could not start counting with it. But it isn't a 0, it's a 2. So 1 through 9. If this is a 1 through 9, you start counting. And once you start counting, you don't stop till you run out of numbers. And now, once you start counting, zeros do count. You just don't start with a 0. Let me say that again. So you start counting with your first non-zero. That's a non-zero, and then you just keep counting till you run out of spaces. 1, 2, 3, 4, 5. This has 5 sig figs. 5 sig figs. 1, 2, 3, 4, 5. They all are significant. Over here, look up here, we're on the right side. You start counting with the first non-zero. You can't start with that 0. You can't start with that. You cannot start with a 0, so we only have one significant figure. One sig fig over here. Just that too. Let me give you another example quick. I might get cut off. You have a worksheet practicing this, so I'm going to put two numbers on the board. You figure them out while I'm handing out the homework here. How about 100.00? And let's go 0.0782. Try those two numbers, and I'm going to give you the worksheet due tomorrow. This is due tomorrow. Don't forget about your quiz on all the circle elements. And I'm actually not going to be here tomorrow after 11. So if you guys have labs 6B, I won't be here, but someone will. All right, real quick before the bell rings. 100.00. How many sig figs? 5. 1, 2, 3, 4, 5. We're starting here. They're all significant. What about here?
3.
We're starting here. 1, 2, 3. 3 sig figs. Skip that 0. All right, this is what you're doing for homework, okay? Telling me how many sig figs they have. All right? Oh, and I will be at the school if you need anything. Good work today.